Yeah, welcome back to the afternoon session of 1%. And we are very happy to have Dr. Manjari Bagchi as the speaker here. She joined IMSE last year, 2 years ago.
2 years ago.
2 years ago.
Thanks.
And she brings to us new area, astrophysics. And she's going to tell us about a sensational discovery that's been made last year of gravitational waves. Manjari.
Okay, thank you. Okay, so good to see so many people. So maybe we can switch off those lights. Okay, so because why we are interested in gravity, right? We know gravity, we feel gravity, right? This is gravity. So what is gravity? So you all know what Newton told us, right? What is gravity? Who can tell you? Force, right? Between two particles. And the attractive force, what does it depend? It depends upon mass of the two particles, means, and square inversely proportional to square of the distance. And because of gravity, that my key ring fell. We are all on earth, fruits are falling, earth is orbiting around the sun, moon is orbiting around the earth, right? That we all know. But okay, tell me that Newton's law said that means two particles, the force between them equal, right? So the force on earth because of sun is equal to the force on sun due to earth. Then why earth is moving around sun, not the opposite? Mass, yes, because sun is more massive. So if the mass were equal or almost equal, then what would they do? They would move around a point in between, right? If two particles were exact, or two bodies, two objects were almost exactly same mass, that point would be just in the middle. And if one become massive, so that middle point, which we call center of mass, would shift towards the more massive. Okay, so we know, and we know that means like the earth is rotating around the sun or all other planets, right? So their orbits are not perfect circular, right? You know that orbits are elliptical. So if you study, means this we call classical Newtonian gravity. So it says, okay, say two objects, means they are on, they say planet, it is moving around the sun in a elliptic orbit. Now before Newton, Galileo came, right? And Galileo discovered its telescope. So people started to, means those planets, they are far, but if you observe for a long time you can see their, means when they are moving in the orbit, you can track their orbit. Very interesting thing they saw, means especially for Mercury, that if you believe in Newtonian mechanics, say my hand is ellipse. So the planet is moving in the orbit, right? But the orbit should remain fixed. But for all planets, the orbit is actually precessing. And that precision was largest for Mercury. So people thought, then realized, okay, so Newton's law, when we apply to do how a planet is moving around the sun, we consider only sun and that planet. But actually there are so many, not so many, means if you include Pluto, 9 planets and then asteroids and other things, right? They also affect. So that, and that actually explain why this orbital movement, what we call precession, is largest for Mercury, because Mercury is the closest, right? Means closest to the sun. So effect of all other objects is one side. But for something which is in between, there are few objects which is towards sun, few is outside. So they balance somewhat. Okay, but it was seen, see this is the total observed, means and this rotation is very tiny. This is 574 arc second per century. So do you know what is arc second? So degree is unit of angle, right? So in 60 arc second, 1 arc minute, in 60 arc minute we get 1 degree. Means sometimes people don't say that arc, means you can only say second or minute, but that might be confusing with unit of time, right? That is why you should say arc second or arc minute when you say it as unit of subunit of angle. So this 574.64, that could be explained as a result of other planets like 531 arc second and the sun. Sun is not a point particle, right? Sun is actually even not a sphere. Sun is like a American football or rugby ball. So if you consider that, that also gives rise to some contribution to the precision. But still little bit remain, that is almost 43 arc second per century. That in Newton's era, even long after that, people could not explain. So let us wait for a bit until Einstein comes. So that was not only one problem. Means physics is evolving, there are new discoveries in physics. So probably you know that around 1861, Maxwell, means Newton first tried to explain what is light, right? Corpuscular theory. But then when Maxwell came, Maxwell said actually better physics is light is electromagnetic wave, right? So actually means you can explain that there is an electric field say along this direction, magnetic field this direction, and wave is perpendicular towards you. That is electromagnetic wave. And not only light what we see, we know that light spectrum VGO, right? That is our spectrum. But there are electromagnetic wave infrared. It means you see this curve, this is longer wavelength and this is shorter wavelength. So if you go longer wavelength, after your visible red, you get infrared. Then you get microwave, which you use in cooking. Then radio waves, you transmit radio message. Then in the other side, shorter wavelength. Shorter wavelength means higher frequency, right? You get after violet, you get ultraviolet, then you get X-ray, then you get gamma rays. So that is the result of Maxwell's theory. But you know all physics theory comes with lots of equations and other things. So Maxwell equation you will learn it when you study BSc physics. So those are vector, I will not mention. But the problem is that, see, all waves means when there is wave in water, it travels through a medium, right, water, or sound wave. I am talking, you are hearing that sound wave, this is the air wave, right, compression and dilation. So what is the wave this light is traveling? Okay, in our atmosphere, this laser point, it is, I can say it is traveling through the air. But we are seeing light from sun, and not only from sun, so much distant stars, even which are beyond our galaxies. There is only empty space. So what is the medium through which light is traveling? Because Maxwell's theory needs some medium. So people thought that okay, maybe there is some kind of medium which may be too dilute or maybe don't interact with anything. Let us call it ether. So there is the proposal of a hypothetical medium ether, and then but as a scientist, you can say something that, okay, there is a medium in the empty space, let us call it ether. But you have to experimentally prove that ether exists, right? Then scientists started to try lots of experiments to detect ether. And basic principle of ether was like that, detecting light velocity in different direction. You remember, say, when you swim in a river, means if you swim in one direction, you are swimming in the direction of flow of the river water, right? When you do in the opposite, your resultant velocity will be lower. So that was the principle people were using. But they failed again and again, so that became a problem in that century. So we have two problems. Why? One is related to that precision of Mercury's orbit, another ether. And that time Einstein came, and you see it is just more than 100 years. Einstein said, okay, I am proposing a theory. So, and he gave all the mathematical derivation. Let us call it special relativity. What does special relativity says? It says lots of things. All he showed with simple mathematics. First, laws of physics is same everywhere. Means I am doing one experiment here, what the result I will get. If I go to a spaceship or I go to Jupiter, I have to correct if it is gravity experiment, I have to correct for Jupiter's different gravity, but laws of physics are same. Okay. Another thing, he said the electromagnetic wave does not need any medium to propagate. It can propagate through vacuum, and speed of light through vacuum is constant, and this is called c. You know the value? I guess you all know, right? Yes, amazing. So that actually came from Einstein and special relativity. And another thing he said, that we should not talk about space only. Space and time are equal. So we not equal, equivalent. We should call it space-time always. So like say, probably you have studied coordinate geometry, right? So if you have 2 points, say coordinate of one point is x1, y1, another x2, y2. What is the distance? Okay. So, and if you have 3D, there will be one z, yes, z2 minus z1 square, and then root over whole. So if you include time as a same footing, so you can measure, you can put one point here today and another point there tomorrow. So you will have T1 minus T2, means difference in time also. So that we call the distance between 2 points. But see, when you write the equation, the units are different, right? The unit of your distance, say in CGS, centimeter or meter. So, but the unit of time, second, right? So you cannot write an equation involving quantities in different unit. So you need something. So if you multiply by c, so c is constant, right? Light velocity. So unit of c, say I am talking CGS, centimeter per second. Multiply it by unit of time, second. So centimeter by second into second. Second will go away. Centimeter, unit of length. So that is called space-time metric. So you see that here means, so far we have three in special relativity. It's 4-dimensional space-time. And here means you consider that when you were 2-dimensional, you had a flat paper, then you go to 3-dimensional, still everything is flat. But when we will talk soon about general theory of relativity, when we consider curvature, that means space-time is curvature. So here you see that you had y2 minus y1 means inside this whole square root y2 minus y1 whole square. When you talk about curved space, there will be terms like y2 inside the square root, y2 minus y1 into x2 minus x1, and there hello. So, and all those coefficients together we called metric, space-time metric. So, that also you will learn, not probably in BSc, but definitely in MSc. And so, up to special relativity, that problem with ether was solved, because Einstein said that electromagnetic wave does not need any medium. Ether does not exist, ruled out. But Einstein could not say with his special relativity about that extra precision of Mercury's orbit. I made a mistake. Can you notice what I did? I said 2015, right? It will be 1915. So, 10 years after special relativity, Einstein came with general relativity. So, that time he first said that space-time is curved, and he said, oh, what Newton said, that gravity means attractive force between two particles, that is just a simplified assumption. Newton, you are not right, you just told us some children's story. It is actually, if there is a body, there is an object, it curves space-time. That is gravity. And if that curve, so, and in Newtonian gravity, one particle moving towards another particle, I said that attractive force is moving it towards. Here I can say, okay, there is a curvature, like say one curved drain like thing, other particle just rolled through the curvature. So, motion of a body means the body is just following the curvature of space-time, and the body which is moving, that is also curving space-time around it, right. So, it is like a loop, means when you have a mass, it is curving the space-time, and then object is moving, means it is following the curvature of space-time, and that movement is again creating change in curvature. So, it is very, and here the more is the mass, the more is the curvature. So, here I see, means it is like a graph paper, like means you cannot view in 3D. So, like graph paper in flat space time. So, you can see that this is a tiny object, little bit curved. Here another more massive object, more my graph paper is more curved. This is more massive object, more curved space time. And we will see that curvature depends mostly upon the mass, means it does not depend that much on its size. So, there can be, means we will talk, means like there are objects say which are equally massive or more massive than sun, but much very tiny. So, they might be tiny, but as they are more massive than sun, we will talk in this next part, we call them compact object, because they are compact, they are very dense, they curve space time very much. So, those type of object can be neutron star, black hole, probably you have heard about black hole, right. And I think you can recognize this picture, right. Yes, it was used in Interstellar. And amazingly, you know who did, this is not a picture, it is actually a computer program was written, it is actually mathematical model. And the person who did it, he is a physicist, he studies, his name is Kip Thorne, he studies general relativity. And he first, okay, we will talk about gravitational wave, he contributed a lot in the research of gravitational wave. To understand gravitational wave, we have to understand this space-time curvature little bit. So, I said that I have a body means because of mass it is curving the space time. And if it moves, means motion means just not motion like this, motion means spin is also motion, yes, rotation, or in physics term we call it spin. You know that cricket ball spins. So if an object is spinning, it changes the distortion. So the same mass object, if it is not rotating, curvature is something, but if it starts spinning, curvature becomes different. So that actually helps to give rise to gravitational wave. So you can imagine like that, say I put a stick on water and I disturb the water, so you get a wave on the water surface. It is something like that. You have a rotating or moving object, and that curvature is moving. So the space, there is some invisible wave in the space, and that I say that curvature of space time is actually gravity, right? So this is a time, so that wave in space time you can say that it is a time varying gravity, right? And gravity is very weak, right? So you need special technique to detect that, we will say. But you know, gravity is very weak, right? If it was not very weak, then our feet is more closer to earth than our head, right? We would stretch, and if we would lie down, our length would change. So we know gravity is very weak. So that is why we needed special technique. But before going to that, I have some animation for you. So because here I cannot do the means what? Okay, so it is someone was. So this is a rubber sheet, right? Or you can imagine this is one plane in the space time.
There's literally a spandex.com class for space time.
So you can see two balls. So when he puts two balls, this flat space is getting curved, right? So one ball, space time is getting curved. Another ball, space time is curved here, and they are following curvature. So that is gravity. It might seem they are attracting each other. They are not attracting each other. This is gravity. Huh? Okay, just 1 minute.
Those two balls,
Huh?
once curved, they come closer to each other only because of Earth's pull, right? Earth's gravitational pull in the classroom.
Yes, even you could do this experiment somewhere. Means here Earth's gravity is creating the curvature, right? But then say if you did not have gravity, you do it in space, then instead of this rubber sheet, this is actually very good question. I am very happy because people never ask me this question. So that time, instead of rubber sheet, you would need a plastic which is curved, because this is real material, right? Because here those balls are very tiny, they cannot curve. But say instead of putting a ball, if I had a plastic sheet which is by default curved, then I could put a ball which would follow the curvature and go to the. And now you will see any other question?
Yeah, poor mass is going to.
It is a very massive. Okay, neglect this wobbling thing. Now he will show orbiting, because for orbiting you need some tangential velocity, right? It will only show that if you have tangential velocity, that can overcome the curvature. So now. He is saying that planets. we could. Now just look at his hand, how he, yes, see now it is orbiting. Now you see one unphysical thing, means orbit is getting closer and closer, and finally it come close to the other object and it merges. It is happening because here he has a physical object, right? There is friction of the rubber sheet. Because of friction, that ball, it is losing energy. So in like Sun Earth system, it is, there is no friction, so no loss of energy. That is why they are moving. But as I said, that there is gravitational emission of gravitational wave, right? That actually came from mathematics of, yes.
In this analogy, the rubber sheet is two-dimensional.
Yes.
And the objects are three-dimensional.
Yes.
But space-time is four-dimensional.
Yes.
And the objects rotating in it are three-dimensional.
Yes.
So how can we compare?
You can compare that this rubber sheet as one cross section of your, forget time, because time is, here also time is coming, right? Time is evolving. Now 3D versus 2D. Object is 3D always, right? But here rubber sheet you can consider, there is one, so you can consider infinite number of rubber sheet, right? And if you put object, so this was the rubber sheet below it, but the rubber sheet, you can imagine one rubber sheet is going in between through the material, right? And so say this is the material, rubber sheet is coming, but when it is entering, it is getting curved. Another is coming, it is getting like this. It is coming, getting like this. Even here you cannot show that you put a ball, and if you keep a rubber sheet top of the ball, you cannot, in this experiment you cannot get curvature, right? But in reality, space-time just top, because that is actually the bottom, right? You can say this is north pole and this is south pole of the object. So here also rubber sheet, it is coming, it will get curved. This is just to visualize. Okay, any other? Yes?
So a body, like it curves space-time, right? Like, so which should attract more bodies to it to cause a bigger curve. So over a span of time, it will attract more bodies towards it. So shouldn't the whole universe collapse upon itself?
Pardon?
A body curves space-time.
Yes.
It attracts more bodies towards it, right?
Yes.
Yeah. So it will create a bigger curve. So upon
Create a?
bigger curve in space-time.
Okay, so there is a body, right? So if it attracts another body, yes, so say here it is, I have curvature, here there is a curvature. So when it is coming, your curvature is coming, your curvature is coming, your curvature is coming, your curvature is coming, they are together. So that means the curvature is larger here. Is it the question you asked? Yes. So there is something, actually universe is expanding, right? Universe is not even steady. Universe is expanding. And it is not only, say, expanding means you can have a expansion velocity that could be a constant velocity. But even that is not true. Universe is actually accelerating, means that expansion of universe is accelerating, and that we don't know why. So the scientists say there is something, some repulsive force, repulsive energy that is called dark energy. And what is the origin and nature of dark energy after Big Bang? Nobody knows. So This is a very open area of research under what we call physical cosmology. That is an amazing question. So probably when you are doing PhD or you are a scientist, you will tell us what gives rise dark energy. Okay, great. Any other question? Yeah, tell.
Like electrons, planets also move in a fixed orbit. Then how can the universe collapse? Like planets, like electrons, the planets are also moving in a fixed orbit.
Okay, so my planet is orbiting around sun, right? But there are, say in your galaxy, there are lots of stars, right? They are not gravitationally bound around each other, right? So if they come close together, they should collapse, right? If there was no dark energy. And again, there is some difference between your planetary analogy also, because it is not, planets are not quantum mechanics. Means when you study electron orbital, there is something called Pauli exclusion principle. Hey, any other question? Tell me the question. So there are some other quantum mechanical effect in atomic structure also, which is not valid. But again, even if it was, again then two stars, nothing kept, actually they collide. Okay, so any question? So what we are saying, that you saw two objects moving and the smaller object came together the closer object, because in this rubber sheet experiment, because of friction it was losing energy. Now I said that ripple in space time, it is gravitational wave. So like our electromagnetic wave carries energy, water wave carries energy, this gravitational wave also carries energy. And because of that, if this amount of gravitational wave is significant, those binary objects, means two objects orbiting around each other, we call them binary objects. Binary orbit would collapse. So why? So you would say, okay, so Earth is rotating around the sun, Earth should emit gravitational wave and eventually it should collapse with the sun. No, because gravity is very weak and Earth is a very tiny, very light object. Yes, Earth is light object, right? But when you have very massive, say, two very big black hole, and you know this, because sun is something we know very well. So in astronomy, we call 10 times solar mass. So unit of mass of sun, radius of sun, those we use as, so many times I will use m sun. M sun means mass of sun. Do you know, any idea what is the? It is 10 to the power 30. You know what does 10 to the power 30 means, right? 30 zeros after 10. So 10 to the power 30 kg mass of sun. And when I said 2 solar mass, that means something whose mass is double than our sun. So say I have 2 black holes. Actually black hole masses are even larger. It can be 10, 100 and even 1000 times solar mass. 2 black holes orbit, for some reason they came close and become gravitationally bound and they had some transverse motion, they are orbiting. So they would emit significant amount of gravitational wave, which actually recently they detected. But because of that gravitational energy, that amplitude is significant, they carries lots of energy, much larger than what the gravitation. Huh?
But the range of the gravitational waves is small. Inside that wave, then inside that region is very large, but outside that region is very small.
What is the, it is wave, right? So like say we are inside water, you just poke a stone there, the wave will come and wave will come. So range of gravity might be, but this wave that is propagating. So it is like crust and it is moving. So that is why we saw gravitational wave from, and another thing say, when water wave, it after sometimes it just subsides, right? But gravitational wave do not, because gravity is very weak, they don't interact. So even if, means say from a large galaxy gravitational wave is coming, it is interacting with lots of matter, but it is interacting very weakly. So it is, amplitude is still high when it is coming. So and because they are losing the energy, those two objects, they are coming closer together. And when they come close together, they actually start rotating faster. That is something we call conservation of angular momentum, that should remain. So I will show you another very short animation. So two objects moving together, and those white ball, those two objects, and this you see waves, and you see they are rotating faster and faster and coming closer. Becoming faster, coming closer, we are zooming, they are coming closer. Very fast, and they merged. And they are spinning. And now you have a single object. What will be that object depends upon what were the objects before and what were their mass. And did you notice there was some sound in the animation? Let me play. You will see once there will be some sound will start. What does it mean? You saw that frequency of the sound also changed, right? This is actually means gravitational wave is not sound wave, but their frequency is in this region is equivalent to our audible sound wave. So that they actually translated, say I have 200 hertz gravitational wave, how the sound will sound to our ear. So that is the significance of the sound. Any question now? Okay, then. Yeah?
When the gravitational waves, when they travel, how does it affect the place they travel to?
How does it?
Affect the others?
Will come. I will just show you. Because it does not actually affect that much, right? If it would affect very much, then say we are here, suddenly a gravitational wave comes, that means we would feel suddenly more gravity, less gravity. So probably you people are sitting, I am standing here, and if gravitational wave passes, we would all start jumping, right? As if, because sometimes we feel gravity is suddenly increasing, suddenly decreasing, but that does not happen. So that is why the detection of gravitational wave needed, people knew it's when it is almost 100 years, right? 1915, Einstein told us about, gave us the mathematics of general relativity, and from there we saw that means you actually can get very nice wave equation from Einstein's equation, but they could not detect because gravity interacts very weakly. So that is why what they did, they built two very large detectors. Those are called two laser interferometer. So what they did, they had two long 5-kilometer long tunnel, and they put some laser. So laser went in one arm, perpendicular arm. So laser went and came back, laser went and came back, and they sent the laser in equal phase. So both were like, say laser is also electromagnetic wave, right? So crust and would be same, but if the gravitational wave comes, means it's like here means even 0.00 means then you put 100 0, there will be that much change in the length of the tunnel. which we cannot measure. But that will change the phase of two lasers, and that actually people detected. That also actually I can show in a little animation. Okay, so you see gravitational wave is coming.
One vital to be able to ripple. That would mean that if something were
So you see that one gravitational wave is coming. Okay, I will just fast it.
not be here, which was of course the source, gravitational wave, highly energetic.
Yeah, you see those two orbiting and you are getting gravitational wave, right?
Said should happen. How do you test this idea? Well, the map shows that as a gravitational wave rolls by,
So here this is Earth and this is say two objects. So Earth is wobbling, means it's like a ball floating around, and you see means you just see in one rubber sheet, but it is going through Earth also. So Earth is almost like oscillating, and it is very tiny, means to show you things have been shown very exaggeratedly, but those are actually okay. So just let me.
in these detectors, what
So you can see, sorry, that was the map of US, right? So can you see the map of America, right? And they built two detectors, one is northwest and another is southeast, to get the diagonal very large distance. And in both places they had that two perpendicular arms.
do the calculation, you find that the amount of squeezing and stretching be tiny, be difficult. The team has now together in Washington State. Then these detectors 4 kilometer long back.
Yeah, 4 kilometer long, the laser is going, and in both the arm laser you see same phase, one arm and another arm, both are perpendicular. So, and this is gravitational wave coming, so length is oscillating. So they are not in phase, right? They are getting out of phase. So when they come, you put laser going through two detector coming, and then you processes together, they will form something which we call interference pattern. So that is how people detected, and that is actually not very easy. Yes, oh, you know, have heard about LIGO, right? So now we know, I have already mentioned that black hole or something called neutron star or something called white dwarf, they actually emit, when they are in binary, they emit significant magnitude of gravitational wave, and we call them compact object. What are compact object? They are actually dead stars. So stars like sun. Why sun emits light and heat? Because we know there is nuclear fusion, right? Means hydrogen, different hydrogen atoms combine to helium, helium combines to carbon, carbon to oxygen, and eventually you get some iron. But iron is very stable, means in stellar temperature, two iron atoms, they cannot combine together. So that is when you have significant amount of iron, that time there is no more energy generation. And see, when there was a star, means we can say there was, if you want to think as Einstein as curvature, it is okay, but for this stellar collapse, you can, even if it becomes easier, you can think about Newtonian force also. So any massive object, see these things, but sun, what I said, 10 to the power 30 kg, and we call it a light star. There are stars 25 times, 50 times as massive as sun. So for them actually the gravitation between the outside particle and inside particle is significant. So that is why means what is they should collapse. Why they are not collapsing the inside the star? Inside the star means I mentioned that universe is not collapsing because of dark energy, but that is a big scale. Inside the star because it is not collapsing because nuclear fusion is going on. There is lots of energy and this energy is pushing the inward gravitation. But when energy creation stops means no nuclear fusion, it collapses. And when it collapses we get something called either white dwarf or neutron star or black hole. And in you need to learn little bit about nuclear physics and particle physics to know, but white dwarf is something very simple. Someone was mentioning about atomic structure, right? So in atom you have a nucleus, say we have hydrogen and helium atom. Nucleus usually proton, neutron, and here if hydrogen one proton and orbital electrons, right? So if extreme gravity will try to push, but as you said that means Pauli exclusion principle and laws of quantum mechanics does not allow that, means in hydrogen and they can be lowest orbit, but then they cannot come arbitrarily close together. What happens then? Atoms break. You get only nucleus and free electron, and because of Pauli exclusion principle, this free electron they give some pressure against the inward gravity. We call that degeneracy pressure. That also you will learn in your BSc. So white dwarf means positive ion and free electron. But if gravity was much larger, then what will happen? Gravity will overcome what I just said, degeneracy pressure of electron, and electrons will try to come again closer. And now for one element of atom you have volume already less than one atom, right? Now it cannot form again atom with the nucleus. What will happen? Even the nucleus will break. So you will have free proton, free neutron and free electron, and that time Coulomb interaction will overcome. So protons will absorb electrons. So proton positive charge, electron negative charge, they will combine and they will form neutron. That is what we call neutron star. And black hole we do not know, means when gravity is too large, even these neutrons also balance gravity by neutron degeneracy pressure. When that also is not possible, we call black hole, and black holes is very compact, and so compact, gravity is so high, we say that even light cannot escape, right? So we actually do not know what is inside black hole, and there is at present knowledge there is no hope to know what happens to matter when it goes inside black hole. So here is some comparison to see, means show you how their density. So if I have one white dwarf whose mass is equal to one solar mass, means mass of sun, its radius is 7 into 10 to the power 3 kilometer, while the mass of sun is 7 into 10 to the power 5, means 100 times less, right, radius. That means white dwarf is, so you know r cube, right, density is m by r cube. So it is 2 to the power 5 times that. And for neutron star, you see the radius is, it is not my typing mistake. Actually a neutron star of mass equal to the sun has radius only 10 kilometer. So you can really can imagine the density, right? The sun you just squeeze into one 10 kilometer radius object, and same if you squeeze it for black hole, its radius will be close to 3 kilometer. You can visualize, right? You can actually do little algebra and you compare the densities of 3 types of object. But actually you do not It is not that always we have this masses of objects. Means black holes can be, okay, so white dwarf actually you can, scientist Chandrasekhar, you know, right? You have heard, he was from Chennai, right? So he actually calculated that a white dwarf cannot be more, Chandrasekhar, right, more massive than 1.4 times solar mass. So, and neutron stars, similar principle, cannot be more massive than 3 times solar mass, but black hole can be, means because any crazy thing can happen inside black hole. Okay, so these are something that these are photograph of sun in different wavelength, because sun emits in all. And how we see white dwarf, because sun's light, I said that nuclear fusion, right? But in white dwarf there is no nuclear fusion anymore, right? So how do we see? Do you know we can see white dwarf? But that is also electromagnetic wave, right? So there should be some source. Actually, white dwarf we see more in X-ray, and why? It is actually means when it was a sun-like star in past history, it was very hot. It just emits the residual heat. And one famous white dwarf is Sirius B. So you know that the brightest star in the sky, that near the feet of the Orion, that is the Sirius A, right? But that is actually binary star. That Sirius A is not a white dwarf, I mean sun-like star we call main sequence, which still have nuclear fusion. But there is a faint object you cannot see in your eyes, I think I should go fast, which we call Sirius B, and that is actually white dwarf. And with your X-ray image, you see Sirius B, that white dwarf is much brighter than the Sirius A. And this is actually X-ray image of a neutron star. But for neutron stars, sometimes things become more interesting, because means if you study all those mechanism, how neutron breaks and everything, you see, and then you practically when you discover neutron star, you saw it is the truth. So say, do you know sun, there is strong magnetic field of earth and sun also, right? So do you know what is the strength of sun's solar magnetic field? So you know that there are sunspot where magnetic field is higher, right? But average it is say 10 Gauss. So I am old, so I don't say in Tesla, I say magnetic field in Gauss. You people study in Tesla, right? Okay. So but for white dwarf, magnetic field is something 10 to the power 3 or 10 to the power 4 Gauss. So much larger than sun. And what about neutron stars? Their magnetic field is much larger. Means the minimum known magnetic field is for a neutron star is 10 to the power 9. So usually the range is 10 to the power 9 Gauss to 10 to the power 15 Gauss. So you can imagine how so strong. And because of that strong means, and but like Earth has a magnetic axis, right? And you know Earth's magnetic axis is not aligned with Earth's spin axis. For stars also there is no reason that your magnetic and spin axis should be aligned. So say I have a neutron star, so magnetic axis is aligned, so star is spinning, magnetic axis is spinning. And again in your BSc electrodynamics you will learn when there is a magnet spins, it emits electromagnetic wave. So and that is like torch like, and that is also spinning, right? So you look at the, say this slide, say this is Earth, okay? And so this is my radiation from a neutron star. So it is spinning, so it falls onto Earth. So because when it completes one spin, so we see it. We cannot see because neutron stars are very faint, we don't see neutron star and that it is spinning. But say it completes one rotation sometimes in 1 millisecond, or its spin period is range within millisecond to second. So that is how we see them. And for us it seems that neutron star is pulsing, we call them pulsar. So we see, and pulsar actually, you would be interested that first pulsar was discovered by a PhD student, not by a very senior person. So I hope one day you will discover lots of astronomical things. And so far there are more than 2000 pulsars known, and around 200 we know in binary. The rest can be in binary, we don't know. And how we know? Because for pulsar we just see the pulsation, but we can study. Means if it is a binary, sometimes it will come close to you, so light would take less time. When it is far, it will take more time. So we can do lots of studies. And this electromagnetic beam, I said that there is a whole spectrum, right? And theoretically, I can show you that this signal means coming from pulsar, it is all wavelength, but strongest in the radio wavelength. So how do we detect that the point is falling on Earth? We need antenna, right? Dish antenna. And as these pulsars are very far, they are very faint. So you need very large dish antenna. So there I show some dish antenna. So this is the world's largest. Its diameter is 300 meter. Can you imagine? You ran 100 meter right in school sports or 300 meter. So you can imagine. And maybe you have seen this in movies. Contact. Have you seen? James Bond. Yeah, there are two movies. One is a James Bond movie, another is Contact. But this is so big you cannot move it. So this one is largest movable. This is in US. Okay, this is also in US. This is 100 meter. Okay, this is the person just I mentioned who discovered first pulsar, Jocelyn Bell. And in India also we have lots of radio astronomy and pulsar discovery. But in India we use another technology, means instead of building a very large telescope, we built lots of small telescope. We call array of telescope. So this is called GMRT, Giant Meter Radio Telescope, that is close to Pune. So if you ever go there, you can see here in this picture 1, 2, 3, 4, only 4 antenna, all are 30 meter diameter. And by studying pulsar, binary pulsar, you can say that like Mercalli precision, you can see that, because they are also relativistic, right? That precision will also be, oh, by the way, did I explain tell you how general relativity solved the problem of Mercalli precision? I forgot, okay, I will show you. Another, just wait a bit, let me, or maybe I can do it. So say this is on ellipse, right? So my orbit means Mercury is moving along the ellipse, right? And and when you study Keplerian, means this is one focus. So sun should be one focus of the ellipse, right? So that is more curved. So if it is more curved, because I cannot curve like this, right? That means the curvature is same along the whole axis. That is not the case. The case is the curvature is higher in one point, right? So let me try to do it. Okay, so say this is the focus. It is not exactly focus. So I am trying to make more curvature here. Now you see, means I start from here and ends here, but that does not come to the same point, right? So can you see it? So now it will follow another path. So, but when it follow another path, your focus and everything will shift. Then curvature also will shift, right? So that is how it precedes. Sorry, I forgot when I started ZR. So for binary pulsars, this precision is even larger because they are neutron star, right? More compact, more curvature. And this emission of gravitational wave, that I mentioned and showed that LIGO experiment, right? That was direct detection of gravitational wave. But we knew, means why would people build such big experiment? Because from pulsar observation, we knew that Einstein was right, gravitational wave exists. Because what that was actually indirect, because what people say, means we are studying pulsar, we could see that this was the first binary pulsar, again discovered by one PhD student, Hals. So, and I said that by measuring how that arrival time of pulse, we can measure, say what is the orbital period. And they found orbital period is decreasing over time. So, there must be something, right? In Newtonian dynamics, orbital period should be fixed, right? So, they explained that with the help of general relativity, and they said, okay, there is gravitational wave is taking away the energy, it is losing energy. So, that pulsar and its companion coming close together. So, that was indirect detection, and they got Nobel Prize in, they made the discovery in 1975, and very soon they got the Nobel Prize. Okay, but I will go fast because the recent detection in, okay, this was the, this is Hals and this is Taylor. This photo was taken just when they were in university and they suddenly came to know that they got the Nobel Prize. And this I already showed, right, the LIGO experiment, 2 laser arms. And those were the, how the wave looked in the experiment. And another interesting thing, just look at the first 3. So, from analyzing the gravitational wave data, they could tell, means how the wave, the interference pattern look, that there are 2 black holes merged and we got the gravitational wave from them. So, one black hole mass was 36 solar mass, another was 29. So, what should be the total mass? 36 plus 29? 65. But their analysis said that the total mass of the merged object was 62. What does that? Huh? Huh? No. Actually, it was converted into energy. You know E equal to mc square, right? These 3 solar mass become gravitational wave energy. And another PhD student who actually, when first analyzing the data, first realized that there is something is there. There is gravitational wave because I am seeing a pattern, interference pattern. And it also says that scientists are not very boring, always looking at data and always studying. No, being science is fun. See, this fellow, his name is Marco Drago, he does so many things. He plays piano, he writes science fiction. So, yes, you can know about nature if you do research, but that never becomes boring because you will always enjoy, you will be happy, and you will do other things also. And what else? Now there is another concept, LISA. They want to put that, like LIGO, gravitational wave detector, in space. Because see, in LIGO okay, another thing, there are 2 LIGO which both are in US, right? One is northwest, another southeast. There is one detector in Europe that has started working, and another is under construction in India. That, huh? No, actually Hyderabad was one of the shortlisted sites. It will be again somewhere close to Pune, means in Maharashtra, so west of Pune. So that we will call Indian LIGO. So there will be things to do with LIGO, but another concept is that because here you need to put big tunnel, right, 5 kilometer long tunnel. And if you want to measure even fainter signal, you need larger and larger tunnel. That is not very easy, right, to get so much land and because in Earth there can be earthquake, means they did lots of seismic study that area there is no possibility of earthquake and other thing. So there is a concept of put this type of interferometer detector in space, that will be called LISA, laser interferometry space antenna. So, and that no single country can do it, right? You need improved technology, you need lots of manpower and money also. So it is the leading is European Space Agency, but NASA is helping them, and probably India will join. And another concept, you use pulsars. I said stellar pulsars emit gravity, right? But you can do other things. Pulsars are already in sky, right? They are emitting light. So you can use them as detector. Means say I have 5 pulsar and a gravitational wave coming from behind. That will also make the pulsar wobbling, and that will also change how their signal is coming. So that is called another, and there you have no constraint. You can have pulsars throughout. So far our telescopes are big, but not as big to detect pulsar in other galaxies, all the pulsars in our galaxy. But even then they are so far, means you can detect very faint and very large signal there. So this is called PTA, pulsar timing array. So there are 4 groups, one working in pulsar timing array. One is Australian group, they are using all Australian telescopes together. Another European group, whole Europe is behaving like a country now, they are using all European radio telescope together. There is North American, by North America only US and Canada working together. Yeah, I have seen those, right, Arecibo, that James Bond movie thing. And another, I said, largest movable, that is in somewhere called Green Bank. And in India, why don't we do? Because I showed you that GMRT, right? So in India also we have, but unfortunately it is not Asian group, that what we are trying to make whole Asia working together. But so far we Indians are also tracking pulsar to see whether gravitational wave is coming from behind. So there is lots of things to do. Those are the telescopes throughout the world being used for this, we call, there are lots of pulsars, so pulsar array, and we see them for long time, we call it timing. So we call that effort pulsar timing array. So this is the Australian telescope parts, Arecibo, that US James Bond one thing, this is the grid bank, this is GMRT in Pune, and that one, anyone have been? China has just built it, but this is actually very close. In your home, it is in Ooty. There is a small telescope, but so it cannot detect very faint, very distant pulsar, but to track known pulsar, it is very good. So I think maybe you can organize a trip from school or something. So this Ooty telescope is doing also good job. So there are lots of things to do in pulsar astronomy, right? And I'll start, there is an amazing thing is coming up for you when you will be PhD student, square kilometer array. Again, means these days one country alone cannot do any big experiment. You have to forget country. So we are going, humankind are building a array of radio telescope, and actually there will be 3 different type of telescopes to operate in different, I showed you, right, there is a huge range of radio wave, right, 3 different types for different frequency range, and all those dark blue countries, they are all working together. It will be placed in South Africa, and you see India is a part of. So when SK means square kilometer array, and it will be ready, I think, when you do PhD, right? So lots of things to do for you. Okay, so let me stop here.